Okay, in this video, I'm going to start by kind of telling you the ins and outs of what I want you to do for the bridge project for the analysis portion. Okay, the analysis portion will be due on a sheet of paper prior to even beginning construction. Okay, so the first thing that I want you to be aware of is the analysis portion is really just an analysis of the truss. Okay, now if you don't know what a truss is, it is a support structure designed to hold up a bridge. So usually on a bridge, for example, you might imagine that, like, let's suppose you went and looked at the Greater New Orleans or the Crescent City Connection Bridge, right? So if you look at the bridge goes up like this. There's a bunch of support beams, and then all of a sudden it's got to span this large distance where it's covering the river, and usually above that section, there is a truss, right? And it might, I'm just kind of making it up, right? I'm not exactly sure what the bridge looks like. But, it's a bunch of triangles usually, right? Now, you might have interlocking triangles, or you might have, a lot of vertical members or things along those lines. You are essentially going to build two trusses, okay? One for the left-hand side of the road, one for the right-hand side of the road, and you're going to connect them in some way that makes sense to you. And such that it will hold a load, which we will be loading from the center of your bridge, okay? And it will be 100% of the load, right? And so what I'm going to need you to do when you do this truss is I need you to analyze the truss and determine all the forces that are in every single member. And the reason that you're going to do this is that by doing the analysis, okay, you will know which members to reinforce. We'll know how to reinforce each member. Okay, so in other words, each member. Okay, and in other words, you're building this out of spaghetti, right? So spaghetti is, not terribly strong, but whatever, it doesn't matter. It's neither here nor there. Everybody's building out of spaghetti. And so, but some members are going to be prone to breaking, and so you're going to want to be like, oh, okay, that one maybe that one, like if the main load is 100, if the main load is 100 units, maybe you have a unit in here that needs to hold 200 units, and you've got another unit here that only needs to hold, say, 30. So if this one needs to hold 30 units and this one needs to hold 200 units, well, then you're going to want to make that particular one thick, okay? And we'll talk about that as we get to it, okay? Now, maybe the most important thing here is that a member of, the truss is basically, any structural element stretching from one point to another, one point to another, okay? Basically, these are just straight beams, okay? In your case, there will be pieces of spaghetti. Some of you will glue multiple pieces of spaghetti together, which is fine. And that's all they are, okay? We will designate them by letters indicating their start and ending location, okay? Now, one thing we want to know about any particular member, so let's suppose this is your truss. This is essentially the truss that I'm going to solve in a second. This is a Howe-style truss. You may not do a Howe-style truss, since I'm about to do this particular problem. Style truss. Okay. So let's suppose this is your truss, right? And we want to know about a particular member in here. So let's suppose we want to know about this member right here. Okay. So I'm going to draw that member right here, and we'll talk about what it means. Okay. So here's that member. Okay. And we're going to make an assumption for all of these members. And that assumption is that these particular members are what we're going to call a quote unquote two force member. Okay, and that's going to make our lives a lot easier, and I'll explain what that means right now. Okay, so up here at the top, this thing is connected at what's called a pin, which basically means, if you can imagine that where I put that dot right there, there's a nail going right through the middle of it. So this member could rotate like that freely if it wasn't also pinned down here. Okay, and similarly, because it's pinned at the bottom, if it were not pinned at the top, it could rotate this way. Okay, if it wanted to. Okay, now, okay, cool, great. So now it's pinned in at these two locations. It can rotate freely, and this is a fairly reasonable assumption, because, well, basically because you're not going to be able to get enough glue in there to prevent it from rotating easily. So anyway, now that we have made that assumption, let's talk about the forces on it. Okay, so if this is location A and this is location B, the rest of the bridge is pushing on that object in a particular way, right? I don't know what that way is, pushing or pulling on this particular beam. So let's just imagine some directions for the forces at these locations. So let's just have A going off this way, and I'll have B going off in the same direction. Why? Because it doesn't matter, right? I'm just making up directions, right? So let's zoom in and let's see what those forces, what we can say just from looking at that, which really isn't very helpful at all, what these forces are, right? So in the A direction, I've got an AX, or the A force. I've got an A in the X direction, and I've got an A in the Y direction. Okay, for the B force, I've got a B in the X, and I've got a B in the Y. Okay, cool. So now I'm going to do a little bit of Newton's law on you, right? So here we go. So the sum of the forces in the X direction equals mass times acceleration in the X direction. So here we go. So in the X direction, I've got AX, which is right here, and then I've got BX, which is right here, and I don't have any other forces. Oh, I did make an assumption here. We're going to ignore the weight of the beam, which of course is completely reasonable because in this case, the spaghetti is really, really light compared to the forces that are going to be on it, okay? So anyway, so AX plus BX, those are my X direction forces. And what about the right-hand side, MAX? Well, in this case, this particular beam, if the bridge is not failing, they're going to add up to 0, okay? So this is a really important statement because what this tells us is that AX and BX must be, one of them is going to have to be negative, right? Must be equal, and I don't know, a symbol for opposite. Maybe I'll just do like that. Maybe that's opposite, right? Equal and opposite. Okay, so one of these two vectors, A or B, is drawn incorrectly. One of them has to go in such a way that their X component is in the opposite direction. Now I can do the same thing in the Y direction. The sum of the forces in the Y direction equals mass times acceleration in the Y. And we're going to get, again, this thing should not be accelerating in the Y direction. And I'll get AY plus BY. Okay? So if I look at that, then I can, okay, cool. AY and BY must be equal and opposite. Cool. All right, sweet. So if that is all the case, then if AX and BX have to be equal and opposite, and AY and BY have to be equal and opposite, then A and B must be equal and opposite. So A and B must be equal and opposite. All right, cool. So let's go up here and let's think about what that means. Okay, so let's kind of clean this up a little bit. Or you know what? Let's leave A where it is. All right, let's leave A where it is. Fine. If A is right there, then in order for this thing not to move, B is going to have to change. All right, so B can't be here. All right, remember, this is the force of the rest of the bridge onto B. Okay, so here we go. So let's fill that in. And let's do this. So here's B going off this way. It's now equal and opposite to A. Cool. Now what's the problem? Does that look like something that is going to stay still? I hope if you look at it and you look at it right, you go, no, that's not something that's going to stay still. What's going to happen, it seems like, is that this thing is going to spin in this sort of direction, right, if we leave them like that. So there's only actually two directions that can be chosen that will not make this thing spin, okay? And those two directions are like this. Okay, so let's see here. Let me erase it. Or like this. So if I take A, and I need to get rid of it, and get rid of B. Now, note that these two have to be equal and opposite in order for this thing not to move. So there's only two possibilities, okay? And I'm going to draw them like this. The rest of the bridge is either doing this. I'll do this, the first option in red. So it's either doing this and that, okay, which means you can see that that's not going to spin and it's not going to move. Okay, this is the option of tension. That means that this member, AB, is being pulled apart, trying to be pulled by the rest of the bridge. Okay, so that is one option. The other option is that the rest of the bridge is either squeezing this member, okay, here and here. Okay, and that is what we call compression. So in other words, and this makes our lives much, much easier. So there's two options for every single member on the bridge. They may either be being tensed, meaning they're trying to be pulled apart, or they are trying to be compressed, meaning they're trying to be squeezed until they break. Okay, those are the options. There are no other options. We don't have to worry about any other options. So that is what it means to have a two-force member. All right, so let's take that idea, and that's the defining idea of this whole entire project, and let's zoom out and let's look at a... Okay, so here we go. It looks like I've got two copies of this particular truss. So I'll take one of them and move it off the screen. I know why it's there. We need it. We just don't need it just yet. Okay, so this particular truss, which is not being very helpful as far as not being moved. Okay, it looks like this. And this is called a Warren style truss. Okay, and you can look these guys up. And what I would hope when you do that is you see kind of what the commonalities of Warren style trusses. Because I'm about to work on a Warren style truss, you will not be allowed to work on a Warren style truss. Okay, so what we're going to do in your particular project is you're going to hang some load right here. Okay, now it could be tempting to just call that load L. And if that load is L, then it is being supported on the two ends by L on 2 and L on 2. You may do that if you like. However, I kind of prefer the idea of not thinking about this in terms of L, just because you guys are relatively new at this. And we're just going to call this 100, as in 100% of the load is right there. And going up, I've got 50% of the load being supported by each of the two sides, so at A and E. Okay, so that's the first assumption that you're going to make. And yeah, okay, cool. Now what we're going to do is we're going to analyze this particular truss, and we're going to try to figure out the forces held in every single member of this bridge. I don't know if it is obvious to you, but it's obvious to me that if I were to cut this particular member, like if I just, kind of, it was under load like this, and I would just go in with scissors and cut right there, but somewhere between A and B, that what would happen is that this thing would collapse, right? A and B would come together. Meaning, I'm pretty sure that member AB is pushing on joint B, and it is pushing on joint A. Okay, and that is kind of its particular role. Now, you may not be able to see that. You may not know that. I can do this for every member of this whole bridge, but of course I've got a lot of practice, and you guys do not. But let's just suppose you didn't know which way it was going, right? Because the other possibility is that it is pulling, that is acting like a rope. Okay, that member AB is pulling on joint A and it is pulling on joint B. Totally possible, right? Well, in this case, it's not possible, but the bridge would fall if that were the case. But anyway, so you don't know which one it's doing, and you need to know that, right? Because you're trying to design this bridge to not fall. The other thing that you're going to want to know is you're going to want to know the magnitude of this particular force. So you might want to know if it's, say, 50 outwards, meaning it is pushing on A and B, or you might want to know if it's, let's say, 150 and it is pulling on A and B, right? These are important facts that you might want to know. Because, for example, if it was 150, well, that's more than our total load. So we're definitely going to want to reinforce this particular member, right? We would want to add some extra spaghetti or whatever to that particular member. Okay, so there's an idea, okay? So we need to figure out what all these forces are. So here's what we're going to do, and I'm going to show you all by doing some math, which I'm going to scroll over here. I've got, this freshie over here. Okay, and what we're going to do is we're going to work on this particular thing, and it's going to help us to determine all of the forces on this particular object, okay? And this will tell you, kind of give you an idea how to work one of these for yourself. Now, what I'm going to recommend when you do your own, okay, and you'll see I picked an easy one. I picked an easy one, an easier truss to solve for a few reasons, but most importantly, I didn't want the video to be too long, all right? So I didn't want to go too long. However, there's other reasons to do a quote-unquote simple truss, okay? And it helps a lot with the simplicity of the calculations, right? So basically, you get repeated calculations. You kind of just see the same things over and over and over again, okay? So it's up to you how you want to proceed with that particular idea, okay? So I highly recommend you do something relatively simple. You can do some really complicated things even within just the math that I have given you. However, the potential for error goes up. Okay. I'm sure there's some other reasons to do it that way, but anyway, let's zoom in here, and I'm going to show you how to get all the equations that I would want you to turn into me, okay? So let's start by, we're going to load this sucker. It's got 100, units of force here. It's got 50 units of force here, and it's got 50 units of force here. Now what we're going to do, and normally you wouldn't use an eraser for this. You would use, you would just kind of draw these all individually. However, I'm going to use an eraser because I am on an iThing. I can't remember if there's an iPad or an iPod. I don't really particularly care. But what I'm going to do is I'm going to draw a free body diagram of every joint in this whole thing. I'm not drawing a free body diagram of anything else but the joints. Okay? So this will give me what I want. Okay? So now what I want you to remember at each joint, so here it is, I'm going to zoom in on joint A, and I want you to remember that these members, right, every single member is either in tension or compression, okay? So that means I have a decision to make, right? So I'm going to draw a little thing like this, so like cut away the rest of the world, and the force here from joint A to joint B is going to go one of two directions. I don't know which way it's going to go. Right, so remember AB is either pulling, so it's either in tension or it's in compression, okay? The same thing will go this way, so we have a force going it's either pulling in tension or it's compressing like that, okay? And so you need to make a decision. And it doesn't matter what your decision is, so I don't want you to get all worked up about it, okay? So I don't want you to get worked up about it, but what I recommend is that you assume all of your forces are one way or the other. That way there's not so much thinking involved. So I'm going to go like, so I'm going to go over here, and I'm going to draw some little squiggles, and I'll go over here, I'm going to draw some little squiggles to show that I'm cutting away the rest of the world, right? So squiggles, 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 and squiggles, squiggles. Okay, so now that I've done that, what I highly, highly, highly recommend you do is that, so the force from A to B is either like this, okay? It's either in tension or it is in compression, okay? Where the member is pushing on the joints and vice versa for that matter. Okay, so what I'm gonna recommend to you is that you choose a direction. You just do it for all of them. So for example, I'm gonna go ahead and choose that this is going this way and that is going that way. That is force AB, AB. Okay, note I'm going to do this for all of the force. I'm going to choose everything to be pulling. So this is going to be AC, this is going to be AC. This is going to be BC, and this will be BC, BC, BC. Okay, this will be BD, this will be BD. By the way, in naming conventions here, I recommend to just keep alphabetical order, right? So I wouldn't call this DC, I'm going to call it CD, call that CD. Okay, we're going to go this way, and I'm going to get CE, and I'm going to do CE. The reason we do alphabetical order is because it prevents you from accidentally solving for something twice. Okay, so then this is going to be DE, and this is going to be DE. Okay, cool. Now, what we're going to do, so I've assumed everything is in tension. Not everything's in tension. Some things are compression. I already told you AB is in compression, so I already know something is wrong. But what's going to happen is I'm going to assume that they're in this direction. I'm going to act like they're in this direction. I'm going to do everything as if they're in this direction. And if I get a negative sign, that means I was wrong. okay, which is totally fine. Okay, so let's zoom in on this particular joint, and let's go ahead and get the equations for this particular joint. Okay, and at this point, this is just chapter 4 stuff. So I'm going to do sum of the forces in the x equals mass times acceleration in the x. Now, for these particular problems, nothing is moving, so max is always 0. So I'm just going to go ahead and write it that way for every single joint. Okay, so let's see. In the x direction, AC is in the x direction, AC. AB has a component in the x direction, right? So that will be plus AB cosine. And instead of writing 60, I'm going to write theta for now. Every angle in this whole thing is 60. So I'm just going to write it that way. Okay, sum of the forces in the y direction. Let's see, in the y direction, I got AB going up. So AB sine theta. And I've got 50 going up. Plus 50 equals 0. Okay, there you go. These are the equations these are two of the equations I'm going to want you to turn in. Okay, and I'll show you how to solve these later. You should be able to see that because we know theta, we can solve for AB right here. And once we have AB, I can solve for AC because I already know theta. But I just want to focus on getting the equations right now. Okay, and I'll show you. I'll go to the end. I'll go to the end of this thing, and then I'll solve all the equations. Okay, so cool. Now let's go up here, and here we got this particular problem, this particular thing, location B. Where do I want to put its equation? Let's put it over here. Okay, so same things we always have. Okay, so we're going to go in the x direction. Well, I got BD is in the x direction. I got BC is in the x direction, or at least some of it. BC cosine theta. I've got AB is in the negative x direction, minus AB cosine. Well, it looks like I need to know that this is also 60 degrees. So that is also theta. So let's go ahead and put a theta right there equals 0. Okay. And I think, I think I put the sum of f of x and the y in the wrong spot. Okay. So sum of the forces, let's give myself a little bit more space than that. Sum of the forces in the y direction equals 0. Okay, so in the y direction, this is only in the x direction. I got BC and I got AB, and they're both going downwards. So negative AB sine theta, this angle right here, minus BC sine theta using that angle right there, okay, equals 0. Okay, again, these are two of the equations we're going to want to solve. Okay, so I'm just going to kind of work through this systematically. So I'm going to go down to this one. This is easily the most difficult of all of the locations. Maybe I have some space. Where do I have space? I have some space over here to do it. Okay. Okay, let's start in the x direction. I've got AC is going in the negative direction, negative AC minus BC cosine theta. So BC cosine theta plus CD. Okay, cosine x plus, because it's going in the positive x direction, cosine theta plus CE equals 0. That is a longish equation. Okay, and then let's see, and then we got to do the y direction, which is simpler than the x direction in this particular case. Sum of the forces in the y equals 0. And I'm going to have BC sine theta plus CD sine theta, right? So CD is upwards, BC is upwards. They both have the same angle. And then I'm going to subtract 100 equals 0. Okay, that's going to be the most common thing that people are going to forget. They're going to forget your external forces when doing these. Okay, cool. So now we're going to go way up here. Okay, we'll go to this one. Okay, and we've got the same two equations. Okay, so in the x direction, I've got negative BD. Let's see, CD's got an x component minus CD cosine theta. DE's got a positive x component, DE cosine theta equals 0. Okay, that's an equation that we will end up using. Okay, and then negative f in the y, so BD is only in the x direction, CD's got a negative component in the y direction, CD sine theta minus DE sine theta equals 0. Okay, boom, beautiful. Okay, so now we're going to go down to this last one. And what you're going to discover about the last joint that you do is that it is what we would call redundant. Okay, usually these equations, by the time you get here, if you've solved all the others, these become unnecessary, right? So in the x direction, let's see, DE's got a negative DE cosine theta minus CE, because CE is only in the x direction, equals 0. That's an equation. Okay, and then let's see, in the vertical, sum of the forces in the vertical equals 0. So we've got, let's see, DE sine theta, okay, because that's going upwards, positive, plus 50 equals 0. Boom. Okay, so now we have all of our equations. There are a bunch of them, right? They're all over the place. And that is what we are working with, right? Okay, you see some of the simplicity here by using just one angle theta. That made my life a lot easier. You could get away with this by doing everything 45 degrees. All right, so there's a few different ways you can solve these. And I think that if you really want to understand, for example, in math class, why you did a bunch of stuff with matrices. This is a very large system of linear equations, which we use computers to solve usually because it's annoying to do them by hand. And a matrix is the way that we would solve this. So if you want to see that particular method, come ask me and I'll point out how to create a system of equations. You can also talk to the people in Mr. Kiff's class as they will solve this using matrices. I don't think I want to make you guys do that. So that is up to you. Okay, so anyway, what I would recommend is that you're going to start solving these. Okay, I'm going to start here. Why? Because this was a relatively simple corner, right? And what you'll notice is that I have two equations, 1 and 2, and I have two unknowns, okay? And so you want to start somewhere where you have two unknowns, because once you have those unknowns, you know, like if you look up here for this one, for example, we have 3 unknowns. Okay, so, which means I don't really want to start there, right? Or right here, I've got 4 unknowns. By unknowns, I mean forces, right? So I've got AC, BC, CD, and CE. All right, that's annoying, right? So what you want to do is start somewhere where you have as many unknowns as equations. So 2 unknowns, 2 equations down here. And once I solve for some of these unknowns, then I will know AB, so that when I go up here, AB will be known. Right? So that's kind of how you're going to do it. You're going to kind of walk through in a way that will allow you to solve for every location where you stop, okay? So let's zoom in and let's solve these guys, okay? So for example, right here at AC, I can rearrange. Notice I can solve this one right here, right? Cool. So I can go and say, okay, cool. AB equals 50 over sine theta. Got it. Okay, done. Okay, I will note that there's supposed to be a negative sign right there, which means I assumed it was in tension and it's actually in compression. Okay, if I'm stuck on 60 degrees as being my absolute number, right? If I've decided, you know what, I'm doing 60, I don't want to play around with this. I don't want to, I don't want to try to, estimate weight to load held ratios or anything like that. I just, I'm pretty sure that I like 60 degrees. We're going with 60 degrees. Then right here, I'm going to get that AB is negative 57 point, how many sig figs do I want here, right? These are, let's just go with 3. Okay, I think that's going to be fine. Okay, 57.7. Okay, and for future calculations, I'll leave the 3.5 out there if I wanted to hold on to that. Now, I want to note that is a negative sign. And so the negative sign means I assumed it was in tension, but it's actually in compression. So let's go over here, and I'm going to show you what we would do with that once we get it, okay? Now, I have colors, so I'm going to use those colors. So this is in compression. So it means the rest of the body is... Okay, so it's going to be pushing on the members, right? So the member AB is pushing on joint A in that direction, and it is pushing on joint B in that direction. So we will end with a total force of 57.7% of our total load down here. Cool. Okay, So let's go back over here and let's keep solving equations. Okay, so I got AC plus AB cosine theta, and we're going to go ahead and solve that sucker, right? So let's see. So AC plus, in place of AB, I'm going to use this, which means I don't need to worry about these extra sig figs, right? Because I'm not even going to plug in, this number is not going to affect any future numbers, right? So, so in place of AB, I'm going to put negative 50 over the sine of theta, okay, that's this number right here, times the cosine of theta equals 0, right? And if I rearrange this, I get AC equals positive 50 cotangent of theta. Okay, cool. Now, again, that's the exact answer. If you don't care about, trying to fiddle and figure out what the optimum angle might be, then you might just plug in 60, in which case you will get AC equals 28.9% of the total load. Okay, now notice there's a positive sign here. So where I assumed it was in tension, it is in fact in tension. So we're going to go over here. And let's see, so here we go. So AC, joint AC, I assumed it was in tension, and we're going to say that, yes, I was correct. So we will pull those in, and we'll say 28.9. Okay, cool. So already we can tell that joint AB is going to be holding more, almost exactly double, probably exactly double, exactly twice as much load as joint AC. However, it is also in compression where joint AC is in tension. So, I don't know what the relative strengths of spaghetti is in tension versus compression. That's something that you will have to figure out later. Okay, cool. So now we know these two things, right? I know AC and I know AB. So let me just go ahead and highlight those because I'll be coming back to those. So let me, kind of bold this out. All right, that's going to be my answer. Okay, again, you could do this numerically, like you could just use this number instead. However, I like to keep things in symbols as long as humanly possible. So let's go up here. I usually go sequentially when I work these. We'll note that we have three unknowns here. We've got AB, we've got BD, and we've got BC, but the thing is we already know AB because we actually solved it from the last step, right? So we're just going to go ahead and plug that in. Now I note that by doing that, that's going to allow me to do the Y direction first because I already know one of the two things that are in that equation. So let's go ahead and do that. So I'll go negative, and for AB, I'm going to plug in negative 50 over sine of theta, times sine of theta, okay, minus BC sine of theta equals 0. Okay, that's an awful lot of sines of theta. We'll note that these two cancel each other, so that's pretty cool. These two negative signs become positive signs. So I end up with BC equals, let's get a nice 50 over sine theta, okay, which I believe we already knew that BC, 50 over sine theta is, let's see, 50 over sine theta is 57.7, right, boom, boom. Okay, again, I'm going to keep using this one, but this is probably the number you're going to want to report on your diagram. Okay, so 57.7, notice we have a positive sign here. So that means that BC is in fact in tension. Okay, and we'll label the diagram all in one step in a second. But right now, let's go up and do the sum of the forces in the x direction. Okay, so I got BD. Okay, plus BC, which is right here, 50 over sine theta, 50 over sine theta, cosine theta, minus AB, which is negative 50 over sine theta, times the cosine of theta equals 0. Okay, this one's kind of gross. Let's zoom in and give myself a little bit of space to actually work here. I'm actually going to delete a little bit of this because we need some space here. Sorry, buddies. Sorry. We love you. Goodbye. Okay, so let's see. So we're going to get BD plus 50 cotangent theta plus, looks like this is another 50 cotangent theta equals 0. So BD equals negative 100 cotangent theta. Okay, so that's the the answer that we'll use for BD from here downwards. However, if I plug in that 60 degrees, I get BD equals, I get a nice 57.7. Okay, hopefully you're noticing that these numbers are kind of repeating again and again and again. Don't forget that negative sign. The negative sign is hugely important. Okay, so we've got two new results here. We've got BD. Notice this is a negative sign. So BD is going to be in compression because I assumed it was in tension. And BC is in positive sign, and I assumed it was in tension, so it is in fact in tension. So let's go over here to our drawings, to our to our big map of everything that we know, and let's draw these on here. Okay, so BC is 57.7 in tension. So BC is in tension, so it is pulling this way, and it is pulling this way. Okay, so that is going to be a 57.7. Okay, and BD was in compression, so BD is pushing on the joints. Okay, and it is also 57.7. Okay, please note that those numbers, the repeatability of these numbers, is all coming out of the fact that I just chose 60 degrees. Okay, I chose the same angle for everything. If you wanted to play around with that angle, you could, and things would not repeat so nicely. Okay, so let's go over here. Let's see here. We've done that joint. We can come down to this joint. This joint stinks, right? But we can do it. Okay, and I think maybe this is a good time to do so. Okay, so let's go down here and let's look at these particular equations. I'm going to give myself a little bit of space. Okay, I'm going to show some deference to that top equation because it looks like it's got 4 unknowns, although I will note that I already know AC and I already know BC. So there's actually only 2 unknowns, CD and CE. So once I get one more unknown, I will be able to solve this one up here, okay? With a lot of luck, with some, I'm hopeful that I'll be able to solve this particular one down here. It seems highly likely, right? Because I already know BC. BC is 57.7 or 50 over sine theta. So 50 over sine theta times the sine of theta plus CD sine theta minus 100 equals 0. Okay? By the way, this is also will be where you will start to notice symmetry will start to play into effect. If you guess that BC and CD are going to be equal to each other, I would be very surprised if that did not happen. Okay, so notice that the sine of thetas go away, and I'm left with 50 plus CD sine theta minus 100 equals 0. So CD sine theta equals 50. So CD equals 50 over sine theta. So notice 50 over sine theta was BC. CD is exactly the same thing. Notice it's positive. So if it's positive, that means I assumed it was in tension. And it is, in fact, in tension. So CD then equals 50 divided by sine theta, which I believe is 57.7. Okay, positive because it's in tension. Okay, so I'm going to use that. I'm going to go up here, and I'm going to solve this particular equation up here. Noting I already know AC. So AC is, let's see here, 50 over cotangent, 50 cotangent theta minus BC, which is 50 over sine theta, 50 over sine theta times the cosine of theta, plus CD, which we got from right down here. CD is 50 over sine theta, 50 over sine theta, okay, cosine theta, plus CE, which is what we're looking for, equals 0. Okay, cool. Let's see here. So I'm going to start to kind of put these all together. So I got negative 50 cotangent theta minus 50 cotangent theta plus 50 cotangent theta plus CE equals 0. So this one and that one cancel each other out. So CE equals 50 cotangent of theta. Okay. Again, we would have expected some similarities here, and notice AC, CE is, yes, it's a positive 50 cotangent theta, and notice AC was also a 50 cotangent theta, so that's not really a surprise. If I plug in that, 60 degrees, I'll I'll get a nice 29.9, or 28.9, excuse me, 28.9. Okay? Again, notice I'm getting a positive sign here, so that particular unit is in tension, because every time I assumed everything was in tension, so if I get a positive sign, I assume it's in tension. Okay, so I got two more things to add. Both of these, both CD and CE, are in tension. So let's go over here and let's put them on our diagram over here. Okay, so let's see. I've been using red for tension, so I'll keep that up. So going this way, CD is 57.7, and CE is going to be in tension 28.9. Okay, hopefully you noticed that at this particular point, I've got every member except for member DE right here. And DE is a wonderful member, but I've got two more locations that I can solve. So you'll see that we have some redundant equations at the end. Okay, the other thing to note is we already know the answer here, right? Everything is symmetric. Again, I highly recommend a symmetric design because that's going to make your life a lot easier. Plus there's, the load will be symmetric, so there's no reason for you not to design it as such. But if you guess that this is going to be 57.7 in compression, to match that, that is a very good guess. However, let's pretend we don't know that, because, if you make an error, then that costs you, right? So we want to make sure that we do that work, right? So let's go over here, and let's do this particular location here. Okay, again, note that by this point, we know BD, we know CD, okay? So either of these equations will work to solve for DE. I'm going to do the one on the bottom because it's an easier equation, right? So I'm going to do negative, and CD is 50 on sine theta, okay, times sine theta. Oh, we love it when that happens. Minus DE sine theta equals 0, right? So these sines of thetas are going to cancel. And I'm going to get DE equals, got to be careful with these negative signs, right? But there will be a negative right here, and it will be 50 over sine theta, 50 over sine theta. Okay? So, if I plug in that 60 degrees, then DE equals negative 57.7. Now, again, remember the negative sign means that it's in compression. I assumed it was in tension, but it is, in fact, in compression. Okay, so that is in fact what we guessed when we were over here, 57.7. Okay, and so there you go. So that is the whole thing. Now, and that's what you're going to basically turn in. You're going to turn in something that looks like this. Turn in this. Okay, and then you're going to turn in all of these equations, right? I'm only going to look through your work if there's errors in your final diagram, right? I'm really good at this. I can look at your diagram and figure out whether it's right or wrong pretty quickly, okay? But I need to see the equations so that I can figure out what you've done wrong. Okay, so by equations, it's all those things that I boxed the first time around. So like this was an equation, that was an equation, whatever. All right, now I want you to note also that at the end of the day, we've got 3 extra equations based on this design. I've got an extra equation here, I've got an extra equation here, and I've got an extra equation 3 here. Okay, what I want you to note is that your solution set, I'm grading you on correctness here. And so what I highly suggest you do is that you use those equations to figure out if you have done this work correctly. So these are your checks, okay? There certainly are designs that will use up all of the equations. I'm not exactly sure how that would work, but usually there's 2 extra equations. So what you do is you just go in here and you just check to see if your work is right, okay? So here's how we were going to do this. We're going to go into this particular equation right here, number 1. And what I'm going to do is I'm just going to plug in the known values and see if these things do, in fact, add up to 0. So negative BD is negative 100 cotangent theta. Oh, it's negative 100 cotangent theta minus CD. CD is 50 on sine theta, okay, times cosine theta, plus DE, which is going to be negative 50 on sine theta, times the cosine of theta, equals 0. So really, this is a question at this point, really. It's like, if this works, we feel pretty good about our work. Okay, so let's distribute that negative to that positive. We'll get 100 cotangent theta minus, this is 50 cotangent theta, minus 50 cotangent theta equals 0, and that works out. So we can go to check there. So right now we're feeling pretty good about our work, like things are probably working out pretty well. Okay, so let's go and let's try our other two equations. Oh, this one's much easier. So we've got negative dE. What was dE? dE was 57.7. Sorry. I took the shortcut. Negative 50 over sine theta cosine theta minus CE. CE was 50 cotangent theta equals 0. So I'm going to get, let's see, those signs are going to cancel out, and I'm left with 50 cotangent theta minus 50 cotangent theta equals 0. That looks good, so we're feeling great. And then we'll go down here. Ooh, this last one's a piece of cake, right? So dE, so negative 50 on sine theta, okay, times sine theta, plus 50, excuse me, plus 50 equals 0. So the sine thetas cancel, and I'm left with negative 50 plus 50 equals 0. So feel pretty good about that. Okay, and that's how you do your bridge project. Okay, and that was, for me, well, this took an hour, with a little bit of start, but for you, I imagine this will be 2 to 3 hours of work, right? Maybe. Just depends on how well you understand this. Okay, the other thing about simplicity that's really good here, so why simple? Why simple? Okay, and is symmetry. If you can do it, how do you spell symmetry? No, that's not how you spell it. Symmetry. Okay, so obviously if you can get symmetry, it's going to make your life a whole heck of a lot easier. Are you kidding me? There's an M in there? You dogs. You dogs, you dogs, you dogs. You ever have a word that just doesn't look right to you? Anyway, okay, so symmetry can be very helpful. Okay, so anyway, if you have questions, please come to me, but this is the idea. All right, hopefully this was helpful. All right.